Good morning. Welcome to Krishna's classroom. I am starting a new series of lectures. This is on linear algebra. In fact, it's a continuation of a series of lectures that I gave and recorded at the St. Joseph's College, DEVAGIRI, in the early part of this year. That is before the advent of Corona. In fact, the IQAC DEVAGIRI had a plan to record an entire course on linear algebra and put it out for students. We started with it with high expectations, and we completed recording the first 7 lectures. And then this is uploaded on YouTube, and it is available on YouTube. But we could not continue this because of the advent of Corona, and so we temporarily suspended it. Now it appears it may take longer time to get it resumed at DEVAGIRI. And therefore, I thought of continuing the series on Krishna's class so that it is available to the students earlier. Now, the objective of today's talk is to give a brief intro to this series. Now, what I have in my mind is to introduce concept of linear spaces and then talk about linear transformations, especially their matrix representations, and then look at the problem of diagonalization, and then have a look at the type of transformations which cannot be diagonalized. This is the objective of our program. Let me just give a summary of the 7 lectures recorded at the St. Joseph's College, because this would serve you to get going from what I start doing on this channel in this series. And of course, for details, one can always refer back to the 7 lectures that are already available on. Okay. In the first lecture, I started by looking at the addition of vectors. Incidentally, vectors appear in physics. It is something that mathematics took it from there and then looked at the mathematics of it. Now you are familiar with the usual things like displacement, velocity, acceleration, force, etc. And then, to get a model for this, the first thing that they did was, this is all from physics, they did was to give a geometric model of the vector. The vector had three important features, namely, there is a point where it acts, there is a direction in which it acts, and its magnitude. So, point of action, vectors, point of action, direction, and this was abstracted out geometrically. Point of action denoted by O, then you had the direction marked out in space, and then of course the length proportional to the magnitude of the vector, whether it is velocity or acceleration or displacement or force, whatever units it is expressed, the length is proportional to that, using some appropriate scale for the description. So it is abstracted out to a line segment in space. Now the problem is that on the same object, more than one force may be acting, or one velocity may be acting, or one acceleration, more than one acceleration may be acting, and so on. Now the question that you ask is, how do they add up? And this is a physical problem, not the problem of mathematics. This should be very clearly understood. Now physicists, as they think about these kind of problems, they create experiments to study the problem. Initially, from the observations, they make some inferences. Now, to check this more precisely, they devise some experiments and try to quantify the readings that you make from the experiments, and then try to interpret that. There is the beautiful experiment that one does at the +1 or +2 level. The drawing board, pulleys, weights, and so on. I just draw the diagram, maybe you just bring a pen in your mind. And there is a drawing board. There are two pulleys clamped here, and then you have weights attached to these 3 points, say W1, W2, W3, under which this point O, let us think that this is in equilibrium. Now when you start doing some measurements, like, or there is a drawing board, drawing paper, fixed to the board. Start marking out the directions of these three strings, and then along the strings you start marking out distances. Along this direction you mark a distance proportionate to W1. Along this you mark a distance proportionate to W2. Along this you mark a distance proportionate to W3. Then what one does is one completes the parallel. And then it is found that the diagonal of the parallelogram is along the direction of the force or the weight W2. And also found that the distance you have marked along the direction of W2 is the same as the length of the diagonal of the parallel. Now this is an observation purely from physical fact, and then of course as physicists do it, they conduct several experiments and repeat the experiment several times with changed weights and so on, and then possibly observe the same sort of story in all sorts of situations. I think you would have done it in your last weeks. Laboratories 6 by 11 6. And then the inference is that this point is in equilibrium because the force acting in this direction, the force acting in this direction add up to a force along the diagonal of the parallelogram, and which is equal in magnitude but opposite in direction to the force acting along the plane. So they cancel each other, and therefore the point O is in equilibrium. This is observed in several situations, and the conclusion that one draws is that vectors add up by parallelogram. So if you have two vectors u and v, then they add up. I mean, this is I'm drawing it in a plane, but need not be. So you have to complete the parallelogram with those two vectors as sides, and then the diagonal of the parallelogram gives what is called the resultant of these two forces, or these two velocities, or these two accelerations, or these two displacements, and so on. So the moral of the story is that vectors add on parallelogram. This was a big break in understanding how vectors add, how vectors acting at a point. Now, the next step is that when you have several vectors acting at a point, then what one does is that do the natural thing, namely you pairwise add them, get the resultant, and eventually reduce to a single vector, which will form the what is called the resultant of all the vectors that are acting. Okay, so that's the inference that you make. So it is a nice geometric model which can be used with the help of some diagrams, etc. But that is the handicap. It's not very convenient to work. Then of course you use the power of elementary geometry by introducing what are called Cartesian coordinates. You identify you take r cross r with cross at 0. This is the point 0, 0. We introduces Cartesian coordinates for all the. I mean, I'm considering activities in a plane right now, we can generalize it to R3. Yeah, okay. Then what you have is, so let us consider what is the scenario. So you have got two vectors here, and the vectors can be identified with the tip of the vector or the coordinates of the tip of the vector. So this is U, E, then that. These coordinates are U1, U2 in the Cartesian coordinate system. This is V1, V2 in the Cartesian coordinate system. Now apply parallelogram law. You get the resultant. The question that you ask is, what are the coordinates of U plus 2? And a little bit of elementary geometry tells you that this point has coordinates U1 plus U1, U2 plus V2. This can be proved using geometry. I emphasize, this can be proved. So this is the inference set. And now this is, see, vector addition has been now simplified considerably. You don't have to go to draw pictures and then pairwise take the vectors there, go for the result and add them together and replace the pair by the resultant and so on. So that activity is now simplified. So if you have, say, n vectors, say say x1, x2, etc., xn, acting at a point with coordinates x11, x12, x21, x22, etc. So xk has coordinates xk1, xk2. Then you see that the sum of these vectors x1 plus x2 plus etc. xn is given by, so we take the xi to be equal to then x1 then sigma xi is given by summation. So these are the coordinates of the opposite. So it's now very simple, very much like addition of numbers. So the problem has been simplified by constructing what is called the algebraic model of the problem. So this is the content of my first lecture, and then you can also talk about this scalar. The same. The second lecture there was a generalization to R, to R2, R, R2, R. These spaces. And then we did some groundwork for some of the computations that you may have to do, and we looked at the what is called the vector equation of a line vector lines and planes. Then of course, if the line is given in the vector form, then how you convert it into the classical analytical geometry form of an equation of a line. and so also, and backwards. That is, if it is given in the conventional form, then how do you express it in the vector? Now this has been discussed in the second lecture, primarily focusing on R2. Okay. So the third lecture centers on geometry of because for the entire coursework on linear algebra, we will be going back and forth to R3. The R2 and R3 are the visible models that you have for vector spaces, and the advantage there is that you can actually visualize whatever is happening. So we have a detailed look at the geometry of R2, what that space is, and what exactly how the planes look like, how do you get the equation of the plane or equation of the line, and so on, and what do you mean by translation, what happens at parallel translate of lines, parallel translate of planes, and how you get the equations, and so on. And specifically, you observe that the equation of the line is of the form x equal to u plus a, where u is a given non-zero vector, and a is a fixed vector, then the equation of the line is of this form. In fact, you observe that this is essentially say, given a line x equal to tu plus a, there is a line parallel to it given by x equal to, and then this is essentially conceived as a parallel translate along the vector. So u is some vector here. So every point on this is given by u, and then a is some non-zero vector. So you translate it, you get a line in space. Conversely, if you have a line in space, you can go for the parallel line, get the vector form of it, and then translate it back to an appropriate vector. Okay. What are the special things to be mentioned here? One thing that you observe is that the line L and LA. So L can be written as, so let me write U and here. This is, see, LU consists of all those vectors x such that x is equal to u LUA. This is the notation. When A equal to 0, you get LUA equal to LU. So L that's a special case. Now what one observe is that LU equal to LV if and only multi-block okay. That means you have several ways in which this line can be described. The description of this line as in the vector form is not easy. That's important. The second question that you ask is this. You see that if you want to use a vector B here, and then you see that L U A may be equal to L V B, and when does this happen? This can happen. Suddenly you see that. And you see that this is if and only if two things happen. One, A minus B is a multiple of U. So also B is a now this is a beautiful question. When does these two lines become one and the same? In fact, proving this would give you a very good exercise on how to write the proof of proofs of mathematical theorems. The result is LUA equal to LBB if and only if A minus B is a multiple of U and B is a multiple of this. As you see here, A minus B, to complete the parallelogram, A minus B is this is A minus B. A minus B has to be a multiple. Okay. So that's the content of the third lecture, and that in a way, in sort of analysis of this vector formulation of lines, planes and subspaces are done with the objective of probably understanding for the entire spaces. The reason will be more vividly clear later. Okay. What do we do from here? Now we are in a position to generally define what the unit space is. In the abstract formulation, now you see that we have a set of objects on X and a field where R and C are the fields that we generally use, and in general you can work with any field. Suppose you have on X, now this is about the fourth one, so I write that. This is in the spaces. Take X, a set of objects, F, a field, and with the property that there is a map from x cross x to x called addition. It's a binary operation. Fine? Which is addition. A binary operation is actually from a map from x cross x to x. And then there is another operation called scalar multiplication, which is in fact from f cross x to x with certain set of properties. What are the properties? You have first set of properties is that x plus y belongs to x now this is the first statement we have. This is true for every x and y belonging to x. Second statement is that addition is associative. That is the associativity of the addition. Third property is that x plus there is a zero element called an identity vector, which has the property that x, that is, this is associativity. This is identity. And then for every x this is the existence of inverse element. Existence of the inverse element. And then you have for xy that is, this is commutativity. That is, x is an abelian that is the first property. Now we have the second operation. It says for alpha belonging to f, x belonging to x, alpha x belonging to x. Alpha dot x I write as alpha x. And then you have the property alpha of x plus y. This tells you how scalar multiplication interacts with addition. Then you have how the addition on y belonging to x, alpha belongs to f. Here alpha, beta, f, x belonging to x. Now the ninth property is that alpha of beta x equal to alpha beta x. Yeah? So alpha beta x as described here. There is the unique element in F. It writes like this: 1 into x equal to x. Then you have zero into x equal to 0. This is 0 belonging to x. This is 0 belonging to x. 0 belonging to x. Yeah? And so whenever the confusion does not arise, you just write it as 0. It's the zero element of x, or what you call the identity element that you have described in the earlier part of this conditions. Yes, if you have the space, the set of objects x, b, and f satisfying these properties with respect to addition and scalar multiplication, so usually whenever you have a vector space, there is the associated field. Like the field plays a very important. Now then, see, after the definition, I look at several examples. Of course, the zero element, the singleton zero in R is a vector space over R. It's trivial for all these conditions. R is a vector space over R. R2 is a vector space over R. Then you have Rn defined by suppose Rn is defined by 4. addition, of course we define x then x plus y, suppose it is defined as and Cx defined by then this is a vector space over R. More generally, I can simply replace this R by F. Then Fn is a vector space over F. In fact, for every field F, Fn over F is a vector space. Okay. Now this is one of the simple things that follow. In particular, you are interested on Rn and Cn. Because quite often they will be coming in various situations. Then you see that suppose you take the polynomials P over Q. So this is the set of form with the coefficients from F. Then with the usual rule of addition of polynomials and the usual rule of multiplication by a polynomial by a scalar, it forms a vector space. Specifically, suppose you write Pn as the set of all polynomials over that is set of all polynomials of PV less than or equal to K, including V0 here also I think I should write including zero point. Some reason for that it is described in the case there. So what is given in that is several examples on linear spaces to get a feeling for what linear spaces are, and even to say that there are plenty of linear spaces in this space, I mean for worthy of considerations. Okay, that's about the chapter. Now coming on to chapter 5, chapter 5 deals with what are called substances. possible that there are certain subsets in a vector space which are themselves vector spaces with the same addition and scalar multiplication. That means you are looking at subsets of a vector space which are closed with respect to addition and scalar multiplication. In that case, such vector spaces are called subspaces of the mother vector space. Okay? So there are several such subspaces. For instance, a visual picture of this is, if you take R2, R2 can be identified in that way. Now, you see that all lines through the origin or the vector 0 alone forms a subspace. If you take all lines passing through the origin, that forms a vector space on its own. And then, of course, the whole space. So there are three types of subspaces that this has, namely the singleton 0, all lines passing through the origin, that is infinitely many of them, and then this is something of the form a1 x1 plus a2 x2 equal to 0, and then or x equal to something like that, or the whole space. So these are the three types of subspaces that this vector space has. When you go to R3, you see that you have the 0, the vector space consisting of just a 0 element, then all lines passing through the origin, all planes passing through the origin, and the whole space. These are all the subspaces possible. Now on every set, every space, vector space has in it several subspaces. And some of the general results that you can prove are intersection of subspaces in a vector space is again a subspace, or what you call the direct sum of subspaces is a subspace. Now these are some of the results that we can prove. So you have concepts like direct sum, but union of subspaces may not be a subspace. Also, you take two lines which are not identical passing through the origin, you take the union, their union is not going to be a vector space, and their intersection is always a vector space. So in R3, if you take say a plane passing through the origin and a line passing through the origin and their intersection, there are several possibilities. One is that the line does not lie in the plane. If it does not lie in the plane, their intersection is the 0 vector, which is a vector space. Or if the line lies in the plane, then their intersection is the line itself. That's a vector space. So in general, one can prove that if there are two subspaces in a vector space, then their intersection is always a vector space. And given a non-empty collection of vectors, there is always a vector space generated by them, in the sense that the smallest vector space that contains the given set. So that is called the span of the given set of vectors. So these are some of the ideas that are discussed there. So some small results are proved there. Then sixth lecture deals with basis and divergence. In fact, to describe a vector, you need not know all the vectors of the vector space, because you have the power of addition, which can be repeatedly done, and also scalar multiplication to generate new vectors. So, given two vectors, you can generate a number of vectors. For instance, if you just take a vector here, non-zero vector in R2, multiply by a different scalars, you generate a whole line. In fact, you generate infinitely many vectors. Okay, right? And if you are given two vectors here, say this one and this one, not necessarily along the same direction, but non-zero, then by addition or by scalar multiplication, you can generate the lines containing them. Further, by addition, you can get any vector can be written in R2 can be written as a linear combination of these two vectors. You apply parallelogram law. Also, this vector is the sum of these two vectors. So this is some P1u and this is some P2u, and their sum will be this one. So this kind of and you see that in fact it can be done for the whole of R2. Therefore, the knowledge of two non-zero vectors which are not along the same direction will give you will describe the complete vector space R2. That is possible. Okay. So it is in fact you need to know only a smaller class of vectors to generate vector space. Such a class of vectors and such an optimal class of vectors is what is called a basis. In fact, we introduced here the idea of what is called span, linear independence, and we say that a vector, a collection V contained in X is a basis which spans X and Z. That's about a basis. So you have the concept of span, concept of linear independence, and then the concept of basis. Basis is essentially a spanning collection of vectors which is linearly independent. Or in a way, an optimal spanning set is what is called a basis. And in fact, you have on R3 E1, E2, E3 is a basis. There are other vectors that you can have, for instance, 1, 0, 1, 1, 1, and then this is a spanning set. Okay. You can show that this is a linearly independent set and it spans the whole space. Okay, right? So there are several spanning sets which are linearly independent that you can pick in general from a vector space. And in some cases, some spaces you are able to do it with finitely, whereas in some spaces a finitely many set of vectors will not span the whole space. So if you have a spanning set which is finite, then you say the vector space is finite dimensional. If the vector space is infinite dimensional, otherwise. Now this is the definition of finite dimension and infinite dimension. Finite and infinite dimension. These concepts are explored in this chapter. Then of course you prove some wonderful results. Says that if you have a finite dimensional vector space, then no matter which basis you choose, the number of vectors in the basis is always remain the same. In other words, there is an invariant number associated with the vector space, irrespective of what basis you choose for a finite dimensional vector space. The number of elements in that is always the same, and because of that, we call that the dimension of the space. So we define dimension. Otherwise, you call the space infinite dimensional. For instance, PF is an infinite dimensional space, whereas PNF is an n plus 1 dimensional vector space. Fn is an n dimensional vector space over F. One more point that I want to mention here, or I have highlighted there, is that the dimension often depends on the field also. For instance, if X is this is something that you can prove. If X is a vector space over F, and F1 is a subfield of F, then X is a vector space of or linear space of over. So a vector space, a given vector space over a field is also a vector space over any subfield of F. This is something that you can prove. So then the geometry of the space differs. For example, I will give an example to cite an example. C is a one-dimensional vector space over C. C is a two-dimensional vector space over R. C is an infinite dimensional vector space over Q, the field Q the set of rationals contain the elements. So this is a very nice result that we explore in the chapter, and it highlights the importance of the role of the field plays in determining what is called geometry of the space. So, Now we have seen that, or what we have explored so far, says that, you see, you can have several bases for a vector space. Okay. So one of the results that you prove is the following. If X is then X is isomorphic to so what one has is this. You have a isomorphism. See, Fn is an n-dimensional vector space over. X is also assumed to be an n-dimensional vector space over. Now what we are trying to define is a isomorphism. This is defined like this. Suppose X is given, choose a basis, an ordered basis, x1. Now since this is a basis, every vector x can be written as a linear combination of x. What you do is, in Fn, choose the vector n due to C1, C2 plus Cn. Now the order is important here because that's why I said it's an ordered basis. Choose an ordered basis. What you define is associate x. So you define phi of x. You can show that this is an isomorphism. Okay, this is an isomorphism. The way in which we have constructed this isomorphism, it is clear that it has something to do with the choice of the basis. Okay. Now, as I have commented earlier, there are different bases that you can choose for the vector space. Every vector, every basis will consist of the same number of elements if you are working in the finite dimensional basis. Then you see that corresponding to this identification will become different. Because what you have is x here, and y in the picture. Choose a x. Now you choose a basis B. An ordered basis. Then you see that you have a phi which associates x with C1 x1 plus C1 Cn, by which you gain phi of x if x is equal to as we have done earlier. But now suppose you choose another basis. Another ordered basis. Then the same x will be represented by, say, some b1 y1 plus then you have the map sine of x defined by b1. That's another isomorphism. So the same vector has two different representations. Now this is discussed in that chapter, and so you have not just one isomorphism, several isomorphisms. Conversely, if you have an isomorphism, then it determines the basis for x. What does it do? Take Fn. Look at the basis E1, E2, etc. What is EI? EI is written as delta I1. That means at the ith place it is 1 and all other places it is 0. That is 1 and 0 are the multiplicative identity element 1 and the additive identity element 0. Okay. So you have these vectors, this forms a basis for Fn. Now if you are given the isomorphism between x and Fn, phi inverse is also an isomorphism of Fn to x. Okay. And further you have, of course, when I say isomorphism here, it means the following. This is structurally the same as F. What does it mean? That you take phi of equal to phi x plus phi y, phi of that means the map preserves the linearity. That's the meaning of that. Okay, now coming back here. So you have got the isomorphism phi and psi. Now suppose phi is given, then phi inverse is also an isomorphism of Fn to x. What you do? You take E1, E2, etc. En, the standard basis for Fn. Now look at this connection. Phi E1, phi inverse E1, then one can prove that if phi is an isomorphism, then this is a set of n linearly independent vectors which form a basis for x. Okay. Therefore, the concept of isomorphism between x and Fn is equivalent to choosing an ordered basis for x. Okay. Once the isomorphism is given, it fixes a certain ordered basis. Once an ordered basis is given, it fixes the isomorphism. So that's something that we have discussed in chapter 7. And therefore, the multitude of representations for x in terms of Fn is possible. This is one of the interesting features which carry forward our study of x further. Okay, so these are the topics generally I have discussed in these 7 lectures, and what I I am still on the ground because our objective is eventually to talk about linear transformation or linear maps from a vector space into another vector space about the same field. How do they look like and what are the properties that you can expect and so on. But before coming to that, we have to still do some more things about the vector spaces. So that we are still on the ground, we are yet to take off from that, and I think in the next 3 or 4 lectures I will be completing the groundwork, and after that we will be talking about mappings between vector spaces, and that's where a lot of interesting things come about. Okay, thank you very much. Stop here. So this gives a brief introduction of what I did at DEVAGIRI. Now I will continue from here and develop the subject in my own way, which I hope will be useful to understand. Thank you very much.